This is one of the most mysterious sounds in the universe. A billion years ago, two black holes collided at nearly the speed of light. The violent explosion distorted the fabric of space-time with ripples called gravitational waves.
A gravitational wave is literally the stretching and compressing of space-time, as predicted by Einstein over 100 years ago, because mass actually bends space-time, and so if mass jiggles, space-time jiggles as well. So Einstein predicted that there should be a way that gravitational waves exist, but he actually thought that there was no chance that anyone would ever detect them because they were so minuscule.
Then in 2015, scientists at a gravitational wave observatory known as LIGO had a breakthrough.
We have detected gravitational waves. We did it.
We were super happy to be in the era of gravitational waves.
Gravitational waves travel at the speed of light, and they carry information about the most extremely relativistic objects in the universe, including objects like black holes. So at higher frequencies, the ground-based detectors like LIGO are doing a great job of measuring black holes at the solar mass or maybe 100 solar mass scale. But if you really want to measure the most massive black holes in the universe, or even just different kinds of gravitational waves, you have to go to much, much lower wavelengths.
For 15 years, an international coalition known as NanoGrav has been trying to detect gravitational waves at low frequencies using a technique called a pulsar timing array.
We use some of the largest radio telescopes in the world to measure a whole bunch of pulsars and hopefully to directly detect gravitational waves in the universe.
At the end of its life, a massive star gravitationally collapses into its core, becoming a neutron star.
A teaspoon of neutron star material could weigh as much as a mountain, so it's incredibly dense.
Some neutron stars begin rotating rapidly, blasting out beams of radiation. These are pulsars.
The kinds of pulsars that we use are rotating as fast as a kitchen blender. So when it spins, that beam might actually get swung into our line of sight, kind of like a lighthouse. And whenever that beam swings past, we measure a radio pulse.
Gravitational waves can subtly alter the timing of those pulses.
A gravitational wave might come from outside of our galaxy. It will then jostle and wobble all of the space between the Earth and the many pulsars that we look at. So we've effectively turned our little neighborhood of the Milky Way and the millisecond pulsars in that neighborhood into one big detector through which gravitational waves can pass.
In June 2023, NanoGrav released its 15-year data showing compelling evidence for the background hum of low-frequency gravitational waves that pervades our universe.
We have strong evidence for the very first time of what we like to call the smoking gun of gravitational waves at this frequency range.
It looks like noise, almost. It looks like a random signal. And yet, when we correlate the signal with another pulsar and another pulsar and another pulsar, we can pull out this very distinctive correlation pattern that we call the Hellions and Downs curve. And for us, it's the fingerprint of the universe swirling in lots and lots of gravitational waves and adding together into this hum that we measure.
The most likely source of these waves are violent collisions of supermassive black holes, but physicists are hopeful for more exotic possibilities.
It seems strange to say it, but supermassive black holes might be the most mundane explanation for our signal.
We know that most galaxies have supermassive black holes, and we know that galaxies merge. But there's zillion papers that have been put out by theorists already that are explaining this background in terms of like basic and new physics, the kind of beyond standard model physics, strings or new types of dark matter, all sorts of possibilities, and that would be super, super exciting.